On the previous chapter, we did an overview of how satellite communications work and the importance of an LNB in the receive chain. On this video, we'll discuss the different types of LNBs, the main parameters in an LNB specification, and to understand how an LNB works and how these parameters affect the performance. Let's start. LNB types and specifications, Chapter 2. There are three main ways to categorize an LNB. The first one is to categorize the LNB by LO configuration. The second one by the downconversion reference, and the third one is by the operational frequency band. For LO configuration and reference, we can find three types of LNBs. DRO use a dielectric resonator oscillator to generate the local oscillation frequency necessary to downconvert the satellite signal to the IF band used by satellite receivers. DRO LNBs are primarily used with large symbol rate signals since the high LO stability does not affect the proper decoding. PL use a digital phase-locked looped circuit to generate the local oscillator frequencies to downconvert the satellite signal to the IF band. PLL LNBs are mostly used with narrow band signals where LO stability has to be high. LNBs are a combination between an LNB and a feed horn. A feed horn is basically a metal funnel that guides the incoming signals to the actual antenna stop inside the throat of the LNB. The LNBF is mostly used on satellite TV applications for commercial homes, where manufacturing parts have to be at a low cost. Another classification of the LNBs are by their reference. They can have an internal reference or an externally injected. Typically, the reference is a 10 MHz signal that is used to make the down conversion. If the reference is internal, the LNB has this reference internally. The external reference LNB should be provided by an external device such as a satellite modem. A third classification for LNBs are depending on the frequency band they operate. These bands using satellite communications are C-band 4 to 8 GHz, X-band 8 to 12 GHz, Ku-band 12 to 18 GHz, Ku-band 26 to 40 GHz, and Q-band between 36 and 46 GHz. On each band, we list the most common frequency range of LNBs for different applications. We also list buck frequencies ranges on each band for your reference. Transmission frequencies are higher than the received frequencies within the same band. Now, let's talk more about the LO stability. LO, or local oscillator, is an electronic circuit that produces a repetitive oscillating electronic signal. It is used to convert from one frequency to another frequency. LO frequency stability is a critical parameter for LNBs. The LO stability, typically for a DRO type, can go from 500 kHz up to 1 MHz. The LO stability for internal reference PLL types can go from 2 to 500 kHz. External reference PLL types depends on the external reference that is supplied, but can go as low as 20 Hz. As you can see, the external reference PLL type has the most accurate frequency down conversion amongst them, but it depends on the reference that is supplied. However, the choice of the LO stability for LNB depends on the signal bandwidth that is received. In some technical specifications, the LO stability is expressed in parts per million instead of hertz. Parts per million are the frequency variation ratio based on the frequency received. LNBs on multiple bands will have a different parts per million because the received frequency is different, even when the LO stability is the same value. There is a formula that can convert parts per million to hertz and vice versa. On the right-hand side, we show a table that compares the parts per million and hertz equivalent values for a C-band LNB. Another LNB parameters we want to explain are the noise figure and noise temperature. Another LNB parameter we want to explain is the noise figure and noise temperature. Noise figure is the decrease in signal-to-noise ratio caused by passing a signal through a system if the original signal had a noise temperature of 290 Kelvin. Noise temperature is the thermal noise power generated in a conductor, and it is proportional to its physical temperature on the absolute scale, Kelvin. Noise temperature is generally a function of frequency. Both parameters are considered a loss, and there is a formula to convert noise figure to noise temperature and vice versa. For some specifications, noise temperature is used especially for C-band LNBs. Another parameter is the conversion gain. Gain is a measure of a circuit to increase the power or amplitude of a signal from the input to the output. The typical gain of an LNB ranges between 55 and 65 decibel. It is a critical parameter to achieve better receiving quality. The LNB gain does not perform evenly along the multiple frequencies that the LNB operates. Moving on to gain flatness. Gain flatness is a measure of gain variation over a range of temperature and frequency band. Typical gain flatness of an LNB is 5 decibel peak to peak over the operational frequency range and the operational temperature range. P1 dB is the next parameter we want to introduce. When you increase the input signal to an LNB, the output power will be increased by the gain value linearly. At some power level, the gain response of the device will really reduce by a specific amount. This power level is said to be the compression point, quite often referred as 1 decibel compression point. LNB should not be operated at P1 dB compression point because it is where the input signal starts to distort at the output. On the other hand, the figure shows the relationship between the input power and the output power. For the small input power, the output power will be increased linearly as it increases in the input power by the gain value. When the output power reaches P1 dB, the signal will compress 1 decibel from the expected value. The next parameter is the phase noise. It is generated by the conversion oscillator within the LNB, and it is a direct function of the quality of the oscillator. It is an indication of the level of noise introduced to a received signal on various frequency distances from the converted carrier. In a digital system, the bit error rate, or BER, on a satellite receiver will be directly affected by the level of the phase noise on the received signal. The phase noise specification of a LNB is mostly expressed at 100 Hz, 1 kHz, 10 kHz, 100 kHz, and up to 1 MHz, distance from the carrier frequency of the converted frequency. LNB phase noise should comply to IESS 308/309 requirement. On the screen, you can see an example of the phase noise measurement of an LNB. On top, there is a phase noise requirement from EIS. On the screen, you can see an example of phase noise measurements. On the top, you will see a phase noise requirement from IESS 308/309. On the bottom, there is a phase noise measurement meeting that requirement. The last parameter we want to introduce is the voltage standing wave ratio, or VSWR. This is the ratio of incident voltage, or primary wave of voltage present on a transmission line, versus any reflected voltage on any line that may be represented as a result of an impedance mismatch condition, which might cause the oscillation of an LNB. The effect of VSWR on a noise figure of an LNB can be substantial. Perfect match means a VSWR has a ratio of 1:1.